So in this video we're going to look at geometry and in particular angles, triangles and parallelograms. So we're going to revisit some angle facts that we would know already from junior cert, and just to refresh our memories, and also maybe there's some ones in there that you may not be 100% familiar with. So let's go through them all in some detail before we jump into some questions. So the first one is, of course, that angles along a straight line will always make 180 degrees. And here, a pair, if you have two angles adding together making 180 degrees, they are called supplementary angles. So anytime you see the word supplementary, it's always implying the two angles are adding to make 180 degrees. Angles around a point then, of course, making a full circle would be 360 degrees, and opposite angles are equal. Then if you see any time parallel lines, so any parallel lines would be denoted by little arrows. So you always want to be watching out for the following types of angles whenever you see parallel lines. So if you can make an F shape between the two angles, then the corners, like here, are equal. They're called corresponding angles. Now that F shape could be a forwards F like it is here, but it could be a backwards F shape, an upside down F shape, an upside down backwards F shape. So any way at all that you can make that F, any orientation of the letter F, and the two angles in the corners, underneath the corners if you like, are the ones that are always equal. Then the other one you need to look out for again with parallel lines is, of course, if you can make a Z shape. So again, a normal forward Z or a backward Z, and if you can make the Z shape, the angles then in the corners are also equal. These are called alternate angles. And just to say that as well, if you can make a C shape, the two angles here would add to make 180 degrees, okay? They would be interior angles. They would therefore add to make 180 degrees. So then looking at triangles, we have different types of triangles. Of course, the angles in a triangle will always add to make 180 degrees. An equilateral triangle is when all the sides are equal and all the angles are equal. And of course, if all the angles add to make 180 degrees, that means each one of those angles, if they have to be equal, are 60 degrees. An isosceles triangle then is when you have two sides equal, and if the two sides are equal, that means the two base angles are equal. So the bottom of those two are equal. So that's an isosceles triangle. Then a right angle triangle obviously has a right angle in it, and of course you know then it can be denoted by this little box here, or a little L. That would make 90 degrees, and then of course in a 90 degree angle Pythagoras applies, so don't forget that. So your hypotenuse squared is equal to the other two sides squared and added together. And a scalene triangle is one that doesn't have any sides that are equal or any angles that are equal. We call that scalene. So as I've said already, the angles in a triangle add up to make 180 degrees, and following on from that then we have that an exterior angle would equal to the sum of the other two sides. Okay, so an angle out here would equal to the sum of the opposite two interior angles. So I want to talk to you now about congruent triangles. What that means is if triangles are congruent, it means they are exactly the same. They have the very same lengths of sides and the very same angles. They have the very same area. They are exactly the same. Now, if you ever want to prove that two triangles are congruent, rather than trying to prove that each of the three sides and each of the three angles are equal, therefore 6 pieces of information, if you like, trying to prove that all of those sets are equal, you can just focus on 3 elements that then, once you prove that they are equal, it would naturally follow on that the rest has to also be equal. So, for example, if you are able to prove in 2 particular triangles that each of the 3 sides are equal to each other, that one's equal to that one, that one's equal to that one, and that one's equal to that one. Note the dashes here. If you have the same amount of dashes on the sides, it implies that they are equal. So this dash equals this dash, so that side equals that side. These 2 dashes equal these two dashes, so those two sides are equal, and then these three dashes are equal, and therefore the sides are equal. If you can prove that the three sides of a triangle are equal, then that's enough. It has to follow on then that the three angles are equal as well, and they are exactly the same triangles, so they are congruent. So SSS is a way of proving congruency. So is ASA. So again, if you can't prove with three sides, but you do have one set of sides that you know for sure are equal, and two sets of angles that you know for sure are equal, then by ASA, you are proving that they are congruent. So another one then is SAS, so two sides and an angle. Now there's one little stipulation about this one you've got to be very careful. It has to be the included angle. In other words, it has to be the angle between the two sides. If it's one of these other angles over here, that would not prove that everything is exactly the same. So it has to be the angle in between the two sides. But if you have that, you know for sure the two sides are equal and the angle in between them are equal, then you can say with certainty that the two angles are exactly the same. So you can prove congruency. And then the last one is RHS. So if you have a right angle and you have a side and you have the hypotenuse. The hypotenuse is, of course, the longest side opposite the 90 degrees. If you have the right angle, a side and the hypotenuse, you can be sure that you have angles, or triangles should I say, that are exactly the same, i.e. congruent. Proving congruency is a really, really useful way of proving if two things are equal. If you can spot at all that you're dealing with triangles and you can prove in the shapes that the triangles are equal, then by default then everything else that you might be talking about in the question would also be equal. So it can be a very useful way of proving two things are equal. If you can spot that you can just prove with the triangles, then, as I said, it can follow on really nicely that the two things that you're looking to prove to be equal, then from the triangles being equal, they also have to be equal. So there are a number of theorems involving triangles and parallelograms that you need to be very familiar with at Leaving Cert Higher level. You only need to be able to prove 3 of them, which is the good news, and I do that in separate videos. But here we're just going to look at what these theorems are, basically the angle facts. You just need to be very familiar with the result of the theorem. So what the theorem is saying, so you know you can use it as an angle fact when answering a question or using it to prove something. So we're going to look at some theorems now, as I said, involving triangles and parallelograms, and get a feel for the different kind of angle facts we need to be familiar with. Before we do that, I want to look at 3 definitions that you need to be familiar with as well. You may be asked to explain what they mean, so you need to be familiar with the language. So the first one is an axiom. An axiom is a statement accepted without proof. So it's something that you can accept without the need to prove it. So for example, the fact that the angles on a straight line would add to 180 is something we would just take as an absolute fact, because it is. It doesn't need a full rigorous proof. We can just always take that and use that then in a theorem to prove something. To explain then the definition of a theorem is a statement that can be shown to be true through the use of axioms and logical argument. In other words, something that you can prove through the use of axioms, those statements that you can take as actual fact, and then by logic, by one thing leading on to another, we can then assume and prove that the statement, in other words, the theorem, is true. So another word you need to be familiar with is a corollary. A corollary is a statement attached to a theorem which has been proven previously already, and it's just a statement that just follows quite obviously on from the theorem. Okay, so it's a little kind of attachment or add-on once a theorem has been proved, something that follows on obviously from the theorem. And lastly, just to note, in mathematics the word implies means that when one result is established already from maybe a theorem or something that's been proven, then another result follows logically from it. So that's what we mean in mathematics when one thing would imply another. It's something following logically on from an established result. So this one you may not be as familiar with. This is labelled as Theorem 7 on your syllabus. It's not one of the ones you need to prove. And it basically says that the longest side will always be opposite the greatest angle. And therefore the smallest side will be always opposite the smallest angle. As you can see quite clearly in this particular example, we obviously have the longest side, 5, is opposite the greatest angle, and that will always be true in triangles. So the actual theorem states the angle opposite the greater of two sides is greater than the angle opposite the lesser side. Okay, so as I said in layman's terms before, that means the longest side must always be opposite the greatest angle. Okay, so it basically says that the largest angle is always opposite the longest side. Okay, and therefore the smallest angle is always opposite the shortest side. So that's basically Theorem 7, and the converse of that is also true. Now what I mean by converse is sort of the reverse of the theorem is also holds true in this situation. So the reverse of this theorem would be then that you can always deduce that the smallest side has got to be opposite the smallest angle, therefore, and the longest side has got to be opposite the largest angle. Okay, so that's the converse that's always true. The converse is not something that is true for every theorem. So the converse of a theorem doesn't necessarily always hold true. I'll give you just a simple example of that. Say you made a statement that was true, like if it's been raining, then the grass is wet. Now, what about the converse of that statement? The converse of that statement would be if the grass is wet, then it's been raining. And of course in that situation, in that particular simple example, that is not something that would hold true. Just because the grass is wet doesn't mean then that it's because it has been raining. So in that situation, the converse of that statement does not hold true. So do you get the idea of that a little bit? So in Theorem 7, as I said, we do have a situation where the converse is true. So it holds true both ways. So the largest angle is opposite the longest side. And of course, if you can see that you've got the longest side, we can assume then obviously it is opposite the largest angle. And so the converse of Theorem 7 reads, the side opposite the greater of two angles is longer than the side opposite the lesser angle. Theorem 8 then, again this might be one that you're not particularly familiar with, says that two sides of a triangle are together greater than the third side. And this has to happen or it will not make a triangle. So that any two sides of the triangle that you add together, it has to work out to be bigger than the other side of the triangle. So going back to this example here, take any two sides, so we'll take 4 and 2.5, add those together, and it is bigger than the third side, 5. Look at 4 and 5 together, that those two sides added together would indeed be bigger than 2.5, and add these two sides together, these have to be bigger than this side here, 4. Okay, and as I said, if that doesn't happen, if you are given 3 sides and any two that you put together will not be bigger than the third, that would not make a triangle. In order for it to make a triangle, any two sides that you add together must always be bigger in value than the third side. Theorem 16 states, for any triangle, base times height does not depend on the choice of the base. So all this means is, it doesn't matter which base and which perpendicular height of the triangle that you take, it will still give you the same area. You just have to make sure, of course, you always have a perpendicular height. So take this triangle here. If we take the base 16 and this perpendicular height here, then multiply those two together and multiply by a half, you get the area of the triangle. And that has to equal taking this side as the base, and therefore this height of 14 as the perpendicular height, half the base times the perpendicular height here, half 12 times 14, also has to give me the very same area. The same is true for parallelograms, because parallelograms are, of course, the area of a parallelogram is base times height. So the same would be true regardless of which base and which height you take. As long as it is a base of the parallelogram and a perpendicular height, then whichever base and perpendicular height you take will have to give the same area. And that's what's written down as Theorem 18 here. Area of a parallelogram is the base multiplied by the perpendicular height. So just something worth noting here to do with triangles and parallelograms and their area. If you have triangles with the same base in between two parallel lines, they've got to have equal areas, because obviously the height between the two parallel lines, or the distance between the two parallel lines, obviously have to be the same. So if they have the same bases, if you know they have the same bases, then they obviously will have equal heights. And the same is true for parallelograms in between parallel lines as well. So watch out for that the heights have got to be the same. The distance between the parallel lines all the way through has to be the same. So once you know you've got the same bases involved, then it follows through that they have got to have the same area. Theorem 17 states that the diagonal of a parallelogram bisects the area. And the word bisect, if you remember, means to cut exactly in half. So the diagonal of a parallelogram bisects the area. In other words, the diagonal will cut the area exactly in half. So equally into two. Okay, so let's jump into some questions now, just practicing all those angle facts that we've come across thus far. So take this question here. We're looking for the angles G and H. Press pause, see how you get on with this one. So I've drawn it out for myself here, and I can spot straight away that with 2 dashes here, 2 dashes here, and 2 dashes here, that implies that those three sides are equal to each other. So it's an isosceles triangle, this triangle here. Therefore, the two base angles, in other words, these two angles here and here, have got to be equal. So if that one's 60 degrees, take it away from 180, of course, and you're going to get 120. That means those two angles there have got to equal 120. So, and they've got to be the same. So divide by 2, and of course we get that that is angle 60, and that is also going to be 60 degrees. Okay, so G is 60, and then taking a look over at the other triangle, again we've got an isosceles triangle, so that angle is equal to that angle up there, so that's H and that's H. And I've got a straight line here, so if that's 60 degrees, then that's got to be 120 degrees. So again, take that from 180, and you're going to get 60, divide that one by 2, and you're going to get each of these H angles, which is 30. So G is 60 and H is 30. Okay, try this question. So again, we're looking for the values of the angles Y and X. Press pause, see how you get on with this. Okay, so I've drawn another sketch for myself here. And the first thing I'm looking at is in this triangle here. And given that I have 2 of the angles already, I know that the 3 angles in a triangle has got to add up to 180. So 180, take away 80, take away 55, has got to give me my Y, which is 45. So Y is 45 degrees. There we go there. And then given that I have the arrows here, I know that these are parallel lines. And if I know they're parallel lines, I'm going to be looking out for being able to make an F or a Z. In other words, corresponding or alternate angles. And in this case, I can make an F here and here. There's my F. And that implies then that this angle here is equal to this angle here. So X therefore has got to be equal to 55. Now, in geometry questions, it is always worth getting into the habit of explaining your reasoning as you go along, because in a lot of questions on the paper where they're asking you to show or prove things, you have got to be giving that logical argument as you go through. So it's worth getting in the habit of doing that as often as possible. So although this question doesn't particularly identify that we do have to do this here, we can just solve for the angles X and Y. I'm just going to start putting in to get into the habit of doing that with all these geometry questions, I'm going to start putting in the reasoning and justification for our answers here, and I'm going to do that now with all the questions that we do together. So what that means for these is that for our justification for getting y is equal to 45, we were able to deduce that because the angles in a triangle add to 180. And for our x angle, we were able to deduce that it had to be 55 degrees because corresponding angles are equal. Okay, so try this question. We're being asked to prove that the triangles ABC and ADE are congruent. And we're told that AC is equal to AD and that BD, so this line here, is equal to CE, so the length of the line here. So proving that the triangles ABC and ADE are congruent. Pause the video here and see how you get on with this. So this is a typical question because it's a proof question that we're going to have to explain our reasoning as we go along. So I'm starting off with what I've been given. BD is equal to CE. Now just to note as well, there are possibly a number of different ways of proving these kind of geometry questions. So just because you may have gotten something different doesn't mean that you are incorrect. You may have proven congruency in a different way. This is the way I've approached it. As I said, I'm starting off with BD is equal to CE, which is given. And given that BD is basically comprised of the length BC plus CD, and CE is based of the length CD plus DE. Given that we have CD on both sides, take them away from both sides, we conclude that BC therefore is equal to DE. So in other words, that line there is equal to that line there. So we have obviously that side which is given, and now we have this side which we're after deducing has to be equal. Now I'm going to look at this triangle here in the middle, okay? And because I know that two sides are equal, I know it therefore has to be an isosceles triangle. And if those two sides are equal, then the two base angles also have to be equal. So those two angles have to be equal. And so to recap, in triangle ACD, then we know that angle C is equal to angle D because it's an isosceles triangle. Do you see the way I'm explaining as I go along each step of my proof? And given that they are both sitting on straight lines, I can deduce that that angle then is got to be equal to that angle there. Because if you take this from 180, whatever you're going to get is this, and if you take the very same thing again from 180, you're going to get these two that have to be the same. And so writing that then in the correct notation, we have angle BCA has got to be equal to angle EDA because they're on the straight angle or straight line. And now I'm going to deduce my congruency because that gives me the angle, and it gives me the included angle. It gives me the angle between those two sides, which is what I need for SAS. And so this last statement here is very important. So the triangle ABC then is congruent, which is denoted by 3 lines for equality, to triangle ADE, and I've proven the congruency through SAS. So stating that is very important, and that is my proof done. Okay, try this question here. So we have ABCD and BEFG are identical squares. First of all, we need to explain why the angle ABG has got to be equal to the angle CBE, and then we need to show that the length AG has got to be equal to the length CE by proving that the triangles ABG and CBE are congruent. Pause the video and see how you get on with this one. Okay, so I've just drawn a little sketch for myself of the diagram here. And the first thing that we're asked to do is, of course, explain that angle ABG is equal to angle CBE. So I've just drawn out the two triangles here that are related to this. Obviously, I'm trying to prove that this angle here, ABG, has got to be equal to the angle CBE. So that's what I'm trying to show, that that angle there is equal to that angle there. So always get that clear in your head, and by all means don't be afraid to label or mark obviously on your diagram or on the diagram on the exam paper. You can, rather than maybe doing all this kind of notation each time for different angles, don't be afraid to say, you know, that you're going to label them as 1, 2, 3, 4. It's sometimes a lot easier to work with the angles when you're doing that, and I will be doing that as we go forward in a few of the other questions as well, so you can see what I mean, to just make your life a little bit easier. In this case, to make my life a little bit easier, I'm just gonna, as I said, draw out the two different triangles and the angles that I am actually trying to show that are equal. So they're the ones I'm dealing with. And of course, what else do we know? What else were we given in the question? That's always very important to revisit. And what we were given in this particular question was that we've got two identical squares. So that means that all the sides of the squares are equal. So that means then that AB has got to be equal to BE. And it also means that BC has got to be equal to BG, and they're all equal to each other as well. So that means that line is equal to that line is equal to that line is equal to that line. And I've gotten that just from the fact that they told me that the two squares were identical. Now, from the fact that I know I'm dealing therefore with isosceles triangles, I know straight away then that that angle here and that angle here, the base angles of an isosceles triangle, are equal. And that means these two angles are equal, not only just to each other, but to these two as well, because these sides are all equal to each other. So as well as being isosceles triangles in each triangle, they are the same lengths of sides and these angles as well. So now if you know that two angles in a triangle are equal, then it follows through that the third angle also has to be equal. So to put that all down formally then in writing, everything that I've just gone through there. So I know that AB is equal to BG is equal to BE is equal to BC, because that was given to me. I was told that the two squares were identical. And then I can show, now this is what I mean, rather than list them all out, angle BAG, angle AGB, angle, because that can be quite laboursome, I've quite clearly drawn my own diagram. I've said C diagram. I quite clearly labelled the angles 1, 2, 3, 4, and I say that angle 1 has got to be equal to angle 2 and equal to angle 3 and equal to angle 4, because they are isosceles triangles. Okay, so it's just a nice clear way. You label it whatever way you want, make it very clear for the examiner what you've labelled, and therefore use that labelling in your proof is perfectly fine and makes your life a lot easier in the long run as well. So now I can deduce then, because these angles are equal, then the third angle has to be equal. So now I'm going to go back to my original notation, obviously for this one up here, because it's what I've been asked to show. Angle ABG is equal to angle CBE, because the third angle in a triangle adds to 180. So your third angle has to be equal then to each other, because the two other angles are equal, and the three angles in a triangle have to make 180. So there we go. So that's the first part. So now let's have a look at the second part, which is asking me to show that ABG and CBE are congruent, and therefore we'll be able to prove that AG is equal to CE. So we got to prove the congruency first. So this is a typical question. If they hadn't given us the hint to go down the road of congruency, bearing in mind that proving congruency can really help you prove a lot of things. If they had just asked us straight out to show or prove that the line AG is equal to CE, then given that we can break it up into two triangles anyway, it would be a logical approach to go through the congruency route, because the minute we can analyze other elements that's been given to us, and from those facts be able to pull out that the two triangles are congruent, then that means everything else to do with those triangles have to be equal. So these two lines AGCE then also have to be equal. So now they did give us the hint here. So we've got our triangle set up and we've proved a lot already. So let's see what we can do. Which kind of congruency method have we got enough information now for? Is it SSS? Is it SAS? Is it ASA or HS or what? What can we use for congruency here? And so in triangle ABG and triangle BCE, we have AB is equal to BE. We've already deduced this. It's given to us. That's a side. BG is equal to BC. That was given to us with the two squares being identical. That's another side. And we've already shown in part I in the question that angle ABG is equal to angle CBE. So that is an angle and it is the included angle. So we can prove that the triangle ABG is congruent to triangle BCE through SAS. And so then the length of AG has got to be equal to the length of CE. Okay, try this question. So in the diagram we have DX is equal to CX and DF is equal to CE and AB is parallel to CD. Prove that the triangle BCF and triangle ADE are congruent. So always double check the information that you're given and whether or not it is notated in the diagram. So just be careful of that. There might be some bits detailed in the diagram and there might be other elements explained in the question that need to be added into the diagram. So here there's nothing really notated in the question that to show you for example that DX is equal to CX, it's just said in the question, and the same DF is equal to CE. So all these things, and even the fact that AB is parallel to CD, we don't have any of the little arrow notation either on the diagram. So just don't ever just assume that everything's in the diagram alone. There's lots more information sometimes in the questions, so be careful and read through things a number of times to make sure you're clear exactly all the pieces of information that's been given to you. Right, pause the video and see how you get on with this question, and again watch your layout, watch how you're explaining your logical argument and so on. Be as detailed as you can is the key with some of these geometry questions, okay? Okay, so I've done a sketch of the diagram for myself up here, and then what I did was I just put in the information on the diagram that they gave me in the text. So they said that AB is parallel to CD, so I just put in my arrows there, so I know to look out for Z or F angles. That's always important. That's what that parallel notation is going to help you out with. And then also they told me that CE is equal to DF, so I've just highlighted that for myself. Those two lines are equal there. And then we're being asked to prove that the triangle BCF is congruent to the triangle ADE, so I just drew them out for myself there as well. And the other bit of information they gave me was that DX is equal to CX, so that just gives me a little bit of information on this triangle, but of course without the full length that's not really helpful. But just to highlight, that's CX, so that line there is equal to that line there. So I'm just going to highlight that for myself on the main diagram as well. So there we go. So just drawing it all out for yourself and splitting bits up just helps you visually see what's going on. So I'm going to start off with the information that they give me about the fact that DF is equal to CE. So now, although that doesn't help me in the triangles that I'm looking at, because in the triangle I'm looking for CF and DE, but let's have a look at this for a second. So CF is the same as CE add EF. Okay, so the length CE and EF is the same as the full length C to F. And likewise, DE is the same as DF plus EF. So DF and EF would give you the full length ED. So analysing these two, since obviously these are the very same, and these are the very same because we know that these two are also equal, we can deduce then that CF is in fact equal to DE. So we have a side length equal. So now looking in this triangle here, okay, so with the two yellow highlighted sides being equal, in that triangle then I know it's got to be an isosceles triangle, and that means that this angle here has got to equal this angle here. So those two angles are equal. And so that's proving that that angle in the triangle I'm looking at and that angle is equal. So in the triangles I want to prove congruency with, I have angle BCF is equal to angle ADE. So that's an A in the congruency, and I'm just explaining where I got that from. That's because I've got an isosceles triangle in triangle CXD, and I know that CX is equal to XD. And now, because they gave me the information about these two lines being parallel, I can spot some alternate angles here, okay? So that implies, given the two angles I've just been looking at, so this angle, as we know, is equal to this angle, and if I can draw a Z here, I can deduce that that angle is an alternate angle to that one as well. And likewise, that angle is an alternate angle to that one as well. So all of those four angles are equal because of alternate angles. Now, if those two angles are equal up here in this little triangle AXB, then that implies then that that side is equal to that side. Because if I have two base angles are equal, then these two sides are equal. So that tells me that AX is equal to XB. And so angle BAX is equal to angle ABX because they're alternate angles. Okay, so these two angles. And therefore AX is equal to XB, as I've just said, because it's an isosceles triangle. So that means that's equal to that. And now I can deduce that angle CB in my triangle is equal to angle AD in the other triangle. Therefore, and so triangle BCF is congruent to triangle ADE because of SAS. We have the two sides and the included angle, again the angle in between, and that proves our congruency. Okay, so last question we're going to take a look at in this video is this one. So we have ABCD and ADBE, they're both parallelograms. And we're told that if the area of the triangle DCB is equal to 15 centimeters squared, find the area of the parallelogram ABCD first, the area of the parallelogram ADBE then, and area of the figure ADCE. And then the last part is saying if the perpendicular height from A to DC, find that perpendicular height A to DC if DC is equal to 7.5 centimeters. Okay, so pause the video here and see how you get on. Okay, so here's a sketch of my diagram, and I'm told that this area that I've highlighted in green is 15 centimeters squared. So we know then already from our theorem that states that the diagonal of a parallelogram bisects the area. So that means that if that's 15 centimeters squared, then the other side of that is 15 centimeters squared as well. In that parallelogram, that diagonal will bisect the area. So if that's 15, that's 15. So the total area of ABCD must be 30 centimeters squared. So the first answer is 30 centimeters squared since the diagonal of a parallelogram bisects the area. Okay, so the second part asks for the area of the parallelogram ADBE. And so given that we are told that both ABCD and ADBE are parallelograms, then if ADBE is a parallelogram, then that means that AD is equal to BE because opposite lengths of a parallelogram are equal. And so AB is a diagonal there that is bisecting that parallelogram, and since we know that this area is 15 centimeters squared, we know then that this area must be also 15 centimeters squared. So this must be 30 centimeters squared as well. since of course AB is the diagonal of the parallelogram and bisecting the area. Okay, so now the next part is asking me to find the area of the figure ADCE. Well, we have that clearly identified for ourselves already. That's 15 centimeters squared, so is that, so is that. So it must be 45 centimeters squared. And the last part then, if the perpendicular height from A to DC is what we're looking for, if DC is equal to 7.5 centimeters. Well, we have that clearly identified for ourselves already. That's 15 centimeters squared, so is that, so is that. So it must be 45 centimeters squared. And the last part then, if the perpendicular height from A to DC is what we're looking for, if DC is equal to 7.5 centimeters. Okay, so the perpendicular height from A to DC is what we're looking for, that height there. And they're telling me if the length DC is 7.5. Well, we can use the fact that we know that the area of a parallelogram is base times height. The area of the parallelogram ADCB or ABCD is of course 30. And we know the base is 7.5. And then we can easily work out what the perpendicular height must be. Divide both sides by 7.5, and I'm getting 4. So 4 centimeters is the perpendicular height.